Hi, my name is Leen, and in this video I would like to talk about the I3C Peripheral found on the Renesas RA2E2. First, I will provide a general introduction to the RA2 series. This slide shows a high-level overview of the RA2 series. The RA2 series offers excellent cost, performance and ultra-low power consumption. It delivers up to 48 MHz of CPU performance using an ARM Cortex-M23 core. The RA2A1 integrates best-in-class programmable analog for high-accuracy sensor signal acquisition and conditioning. The RA2A1 MCU targets cost-sensitive and low-power industrial sensor applications where high resolution is a must. The RA2L1 and RA2E1 families are general-purpose single-chip MCUs, which support a wide operating voltage range of 1.6 to 5.5 volts with low-power architecture. The products are available with up to 256 kilobytes of flash memory and up to 32 kilobytes of SRAM. Pin counts ranging from 25 to 100. The RA2L1 and RA2E1 group also feature a hardware capacitive touch use sensing unit, or also called as CTSU2, a set of serial communication interfaces, analog and peripheral timers. Newest is the entry-line low-power microcontroller RA2E1, the focus of this video. The RA2E2 offers low pin count options from 16 to 24 pins, together with innovative functions such as the I3C interface and 125 degrees Celsius temperature support. The RA2 series provides extensive memory size and package options with excellent pin compatibility. The RA2L1 is offered with flash sizes of 128 and 256 kilobytes, supporting 48 to 100 pin packages. And as you can see on this slide, the RA2E1 lineup is starting with 25 pins up to 64 pins and flash memory sizes starting at 32 up to 128 kilobytes, including very small package options such as QFN, LGA, BGA and WLCSP. The RA2E2, highlighted in red, covers the low end of the series and supports 20, 24 and 16 pin wafer level CSP packages. Flash memory sizes starting from 16 up to 64 kilobytes. Now in this block diagram you see the RA2E2. It's based on the low power 110 nanometer MF4 process, operating from 1.6 to 5.5 volts, integrating a 1% accurate high-speed on-chip oscillator, and it's specified from -40 to 105 degrees standard or 125 degrees Celsius as an option. The RA2E2 is offered with flash sizes from 16 up to 64 kilobytes and 8 kilobytes of SRAM with parity. The RA2E2 has a 12-bit ADC with up to 8 channels, and there are also 6 16-bit general purpose timers and 2 channels of low power asynchronous timer. There are several communication interfaces including I3C, I2C, SEI, SPI. Hardware safety and security features are also incorporated. The RA2E2 comes in small packages such as QFN and the very small WLCSP of only 1.87 by 1.84 millimeters. Here we see how small the WLCSP 16 package is, only 1.87 by 1.84 millimeters as I said, making it ideal for wearables and other space-constrained applications. No need to go into details here, just about any space-constrained application is suitable for the RA2E2, both for its small size and also extremely low cost. Here you have a short description of the main differentiating features of the RA2E2. The RA2E2 I3C peripheral provides significant advantages in terms of performance and simplicity. I will go into some detail on the specifics of the I3C peripheral in the following slides. One of the most obvious features of the I3C peripheral compared to the I2C bus is the reduction in number of interface wires. Traditionally, the I2C bus only needed two wires, SDA and SCL, but as peripherals became more complex, higher data rates and additional signaling such as triggers and interrupts were introduced. The I3C bus brings simplicity back to the two-wire bus by integrating these additional features into the protocol and increasing the bandwidth to support higher data rates. So what is the I3C peripheral? Also known as the MIPI I3C or SenseWire, it's a technological progression on the 40-year-old I2C standard. I3C actually stands for Improved Integrated Circuit. The I3C standard is designed to retain backwards compatibility with the I2C system, notably allowing designs where existing I2C devices can be connected to an I3C bus but still have the bus able to switch to a higher data rate. For communication at higher speeds between compliant I3C devices, the I3C standard thereby combines the advantage of the simple two-wire I2C architecture with a higher communication speeds common to more complicated buses, such as the Serial Peripheral Interface, or SPI. Incorporating the key capabilities of I2C and SPI into an advanced consolidated specification. Actually, it's the best of both worlds. It's the mix of I2C and SPI. Some I3C advantages. I3C uses the same signal pins as I2C, referred to as SCL for the serial clock and SDA, the serial data. The primary difference is that I2C operates them as open drain outputs at all times, so its speed is limited by the resultant slow signal rise time. I3C uses open drain mode when necessary for compatibility, but switches to push-pull outputs whenever possible and includes protocol changes to make it possible to do that more often than in I2C. I3C supports multiple controllers, but they are not symmetrical. One is the current controller and responsible for generating the clock. Other devices sending a message on the bus, in-band interrupts or secondary controllers wishing to use the bus, must arbitrate using their own address before sending any other data. Some more I3C advantages. So it's largely backward compatible to I2C, and it supports an interrupt master on the bus with a mix and match of regular I2C and I3C slaves, supporting also dynamic address assignment or DAA for I3C slaves, but still supporting static addresses for older I2C devices. But there are a few features not supported by I3C. For instance, pull-up resistors are provided by the I3C controller. External pull-up resistors are no longer needed, generally speaking. Clock stretching. Devices are expected to be fast enough to operate at bus speed. The I3C controller is the sole clock source. And the I2C extended 10-bit bus addresses. All devices on the I3C bus are addressed by a 7-bit address. Native I3C devices have a unique 48-bit address, which is used only during dynamic address assignment. The I3C peripheral supports 5 different device roles. The main master, in which the I3C bus, which controls the I3C bus and function, and includes bus ownership, control and handoff to secondary masters. Secondary master, which takes temporary control of the I3C bus. Slave, which responds to either common or individual commands from the I3C master, and peer-to-peer slave, which can write to or read from another slave without the interaction of the master. And finally, the I2C slave, for legacy I2C devices present on an I3C bus, to which I3C master devices can communicate but whose speed and capabilities are constrained. One of the major advantages of I3C is that it provides higher data rates. It's a two-wire bus, and its SDA signal carries bidirectional serial data, just like I2C. The SCL signal can act as either a clock pin or as a data pin in high data rate or HDR applications. The I3C bus supports a mixture of message types, including I2C like signal data rate messages, which use SCL clock speeds of up to 12.5 MHz, and HDR messages at higher data rates. The data rates supported on an I3C bus depend on the bus mode, the type of devices on the bus, and the capabilities. A bus to which only I3C devices are connected is called a pure I3C bus, and supports speeds from 8.8 to 26.7 megabits per second. Typically, the SCL clock frequency is on a pure I3C bus is 12.5 MHz. If the bus connects a mix of I2C and I3C devices, the I3C master can communicate to the I2C slaves at a fast mode, FM, and a fast plus mode, FM plus, of 400 kilobit or 1 megabit respectively. In a mixed mode bus, the I3C master can still communicate to I3C slaves at up to 20.5 megabits per second. Connecting I2C devices to an I3C bus limits its operating speed to 20.5 instead of 26.7 megabits per second. The I3C standard is still relatively new, and as such there are still relatively few slave devices with a dedicated I3C interface available. However, the major advantages of I3C over I2C are many and worthwhile, such as increased communication speed, lower power consumption, and less wiring. This makes the compatibility with I2C an excellent feature. Currently, the I3C slave devices that are already available are multiplexers, level converters, temperature sensors, inertial measurement units or accelerometers, and Hall sensors. An interesting feature and a necessary feature of the I3C is the in-band interrupts that allow slaves to notify the master. These can be both equivalent to a separate GPIO, but can also be directly data-bearing, prioritizing so that if multiple slaves wish to interrupt at the same time, the order is resolved by the master. Dynamic addresses are used for this, so priority is controlled by the master, obviously. Interrupts can be started even when the master is not active on the bus, and yet no free running clock is needed. Time-stamping option to allow resolution of initial event versus when the interrupt gets through. Mastering, late start and insertion. Organized forms of multi-master. The slave can request the master to allow it to message another slave, yet not needing to generate its own clock. This is called peer-to-peer. The secondary masters, which can use clean handoffs between each master. Hot join onto bus allows devices to come online later than the initial bus bring-up. This may be due to a late wake-up or a power-up or a physical insertion at a later date. And this provides clean methods for notification. I3C bus supports different communication modes. As throughput increases, the energy consumption reduces. Significantly lower power consumption with I3C devices compared with legacy I2C devices. You must note that the RA2E2, being a low-cost device, only supports SDR mode. Renesas provides an example project bundle for all of their RA evaluation boards. These demonstrate most of the peripherals on the device. However, the drivers for the I3C peripheral are included in the FSP since revision 3.40. There is no example project as yet in the bundle at this stage. I will update this presentation at a later date when this is made available. A detailed description of the I3C API is included in the FSP documentation. Here you see a listing of the API calls. This page shows you the microcontroller and kit ordering information. The kit comes complete with an onboard debugger, and all of the pins are accessible through various headers. It comes full with a user manual, quick start guide, development tools, free of charge, schematics, the design files, the Gerbers, and example projects. Typical price for this board is about €55. This concludes this presentation. In closing, I would like to thank you for your attention, and if you have any questions or recommendations for future videos, don't hesitate to contact me on this address. Thank you for your time.